Welcome, tech enthusiasts, to a journey into the microscopic realm that could redefine global security. Imagine a future where weapons are disarmed not by bombs, but by clouds of intelligent microscopic machines. This isn't science fiction. It's the concept of nanobot disarmament clouds, a fascinating and complex intersection of advanced nanotechnology and international arms control. Nanotechnology is the engineering of functional systems at the atomic and molecular scale, typically between 1 to 100 nanometers. To put that in perspective, a human hair is about 80,000 nanometers thick. At this scale, materials exhibit unique properties, opening doors to revolutionary applications across medicine, computing, and, inevitably, defense. This field allows us to manipulate matter with unprecedented precision. We can design materials with incredible strength-to-weight ratios, create highly efficient sensors, or develop targeted drug delivery systems. The implications for both civilian and military applications are profound, pushing the boundaries of what's possible. Within nanotechnology, nanobots are microscopic robots designed to perform specific tasks. These aren't just passive materials. They are theoretical machines capable of sensing, processing information, and acting upon their environment. While still largely in the conceptual and early research stages, their potential is immense. The most concerning aspect for military strategists is the idea of self-replicating nanobots. These are theoretical machines capable of building copies of themselves, potentially leading to exponential growth. This concept, often dubbed gray goo in worst-case scenarios, highlights both the incredible power and the inherent risks of uncontrolled nanotech. Nanotechnology offers a dual-edged sword for weaponry. It can enhance existing weapons, making them lighter, stronger, more precise, or stealthier. Imagine armor that's virtually impenetrable, or sensors that can detect targets with unparalleled accuracy. Beyond enhancement, nanotech could enable entirely new classes of weapons. We could see smart dust sensors dispersed over vast areas, self-assembling munitions, or highly targeted biological agents delivered with pinpoint precision. The ability to operate at the molecular level allows for unprecedented control and destructive potential. Now, let's flip the script. What if this same microscopic precision could be used for peace? The concept of nanobot disarmament clouds proposes using these tiny machines to neutralize weapons systems. Instead of destructive force, the goal is precise, non-lethal incapacitation. Imagine a cloud of nanobots released over a battlefield or a rogue weapons facility. These nanobots could be programmed to identify specific weapon components, such as electronic circuits, explosive materials, or propulsion systems. They could then disable these components by disrupting their molecular structure, jamming their signals, or even consuming their critical parts. The theoretical mechanisms are fascinating. Nanobots could be designed to infiltrate weapon systems through microscopic openings. Once inside, they might target sensitive electronics, causing short circuits or data corruption. They could chemically alter propellants, rendering missiles inert, or degrade the structural integrity of armored vehicles. This approach offers the tantalizing possibility of surgical disarmament. Instead of widespread destruction, nanobots could disable weapons without causing collateral damage or loss of life. This could revolutionize arms control, offering a non-violent means to enforce treaties or prevent conflicts from escalating. Despite the potential, the concept of nanobot disarmament clouds is fraught with challenges and ethical dilemmas. The very nature of nanotechnology, with its dual-use potential and microscopic scale, creates significant hurdles for international governance and control. One major concern is the difficulty in defining and regulating nanoweapons. How do you classify a weapon that operates at the molecular level? Does it fall under conventional arms, or does its potential for widespread disruption push it into the realm of weapons of mass destruction? The lines blur, making existing legal frameworks inadequate. Verifying compliance with arms control treaties is already complex. With nanotech, it becomes exponentially harder. The minute size of nanomaterials and nanobots makes detection and monitoring incredibly challenging. How do you confirm that a nation isn't secretly developing or deploying these microscopic agents? Current verification methods, relying on satellite imagery or on-site inspections, are ill-equipped for this scale. New, highly sophisticated detection technologies would be required, potentially involving advanced spectroscopy or molecular imaging, to even begin to address this challenge. The environmental and human health implications of widespread nanobot deployment are a significant concern. What happens if these nanobots escape their intended targets? Could they interact with ecosystems in unforeseen ways, disrupting natural processes or accumulating in the food chain? Furthermore, the human toxicity of engineered nanomaterials is still being researched. Inhaled nanoparticles can enter the bloodstream and interact with cells, potentially causing inflammation or long-term health issues. The release of a disarmament cloud could inadvertently expose populations to harmful agents, even if the intent is benign. Nanotechnology epitomizes the dual-use dilemma. Technologies developed for beneficial purposes can also be weaponized. For example, carbon nanotubes, prized for their strength in materials science, could also be used to create incredibly durable weapon components. Quantum dots, useful in medical imaging, could be repurposed for targeted delivery of harmful agents. This inherent duality makes control incredibly difficult. How do you restrict military applications without stifling legitimate scientific research and technological advancement that could benefit humanity? The challenge lies in finding a balance that promotes innovation while preventing misuse. The microscopic nature and novel mechanisms of nanobots could potentially allow nations to circumvent existing arms control treaties. For instance, aerosolized nanobots designed to disrupt biological processes might be argued not to be a biological weapon in the traditional sense, even if their effect is similar. Similarly, if nanobots are designed to degrade chemical agents, they might be seen as a defensive measure. However, the same technology could be adapted to create or enhance chemical weapons. This ambiguity could create loopholes in conventions like the Biological Weapons Convention, BWC, and the Chemical Weapons Convention, CWC. Existing international laws and treaties, such as the Nuclear Non-Proliferation Treaty, NPT, or the Outer Space Treaty, were drafted long before the advent of nanotechnology. While some principles may broadly apply, their interpretation for nanotech-based weaponry is complex and often ambiguous. There is a pressing need for the international community to engage in robust discussions and potentially develop new legal frameworks or protocols specifically addressing military nanotechnology. This would involve defining what constitutes a nanoweapon, establishing norms for their development and use, and creating mechanisms for verification and enforcement. Given the rapid pace of military nanotechnology development, increased public scrutiny is absolutely essential. This isn't just a technical issue, it's a societal one. We need open discussions about the potential health, environmental, and ethical implications of these technologies before they become widespread. Scientists, policymakers, ethicists, and the public must collaborate to assess the risks and benefits. Transparency in research and development, particularly in areas with military applications, is crucial to foster trust and prevent an uncontrolled arms race in the nanoverse. A particularly concerning aspect of advanced nanobots is their potential for autonomy. Nanobots could be designed to operate independently, storing information, making decisions, and affecting specific targets without direct human intervention. This raises profound ethical questions about accountability and control. Imagine a swarm of autonomous nanobots programmed to disarm, but then encountering unforeseen variables. Could they misidentify targets? Could they evolve their behavior in unexpected ways? The concept of killer robots takes on a new microscopic dimension when applied to autonomous nanobots, blurring the lines of human control and responsibility. The international community faces unprecedented arms control challenges with the advent of nanotechnology. The potential for mass destruction, or at least mass disruption, from these microscopic agents is immense. Preventing an uncontrolled proliferation of nanoweapons requires proactive and innovative approaches. This includes fostering international cooperation, establishing clear ethical guidelines, and investing in research for defensive and verification technologies. The goal must be to harness the beneficial aspects of nanotechnology while mitigating its potential for harm and ensuring global stability. It's important to reiterate that self-replicating nanobots and large-scale nanobot disarmament clouds are still largely theoretical. Significant technical obstacles remain, including power sources, communication, navigation in complex environments, and the sheer difficulty of manufacturing at such a precise scale. However, the theoretical nature does not diminish the need for discussion. The pace of technological advancement is accelerating, and what seems like science fiction today could become a reality tomorrow. Proactive consideration of these possibilities allows us to shape the future responsibly, rather than reacting to crises. The concept of nanobot disarmament clouds presents a fascinating paradox. A technology with immense destructive potential also holds the promise of unprecedented peace. As tech enthusiasts, you understand the power of innovation, but also the responsibility that comes with it. The future of nanotechnology and its role in global security is not predetermined. It will be shaped by the choices we make today. We must engage in informed debate, push for ethical development, and advocate for robust international frameworks. What are your thoughts on this microscopic frontier? Share your insights in the comments below. Don't forget to like this video, subscribe for more deep dives into future tech, and hit the notification bell so you don't miss our next exploration into the cutting edge.